Okay, so unfortunately we left midstream Monday's class. We did not finish this problem. So we'll go over it now. You'll see this type of problem on the exam. So what are we trying to do here? Okay, so this is called the Clausius-Clapeyron equation. And what this equation does, it relates vapor pressure 1 at some T1, and then we have we change the temperature. Okay, if we change the temperature to T2, we'll get a new vapor pressure 2. Okay, everyone get that? Okay, change the temperature, change the vapor pressure. Okay, lower the temperature for water, you'll have a different vapor pressure for water. Increase the temperature of water or any liquid, and you will change the vapor pressure of that liquid. So this is what we mean to say is that vapor pressure is quoted at a specific temperature. So this is the equation here. I'll give you this version on the exam, but this version is also just as fine. And so this is vapor pressure P1 at T1, vapor pressure P2 at T2. Okay, the P1 over P2 is under the natural log. Okay, delta H vap. What is delta H vaporization? Okay, it's the energy to do what? This is the energy to vaporize how much? 1 mole. Okay, this is the energy required to vaporize 1 mole of the substance. And what do we mean by vaporize? Okay, from a liquid to a gas. Okay, liquid to a gas. And when it becomes a gas, it can go back down and exert a what? It can exert a vapor pressure. Okay, so this vapor pressure is a dynamic equilibrium. Okay, vapor pressure. Evaporation, condensation. Once it condenses, it exerts a vapor pressure. Right, and R is a gas constant, and I'll give you that value. Okay, so really you don't have to memorize anything, you just need to know how to use it. All right, shall we finish up this problem here? All right, so we have ethanol, and the vapor pressure is 100 millimeters of mercury at 34.9 degrees C. What is the vapor pressure at 63.5 degrees C? Okay. So the first thing we want to do is convert kilojoules per mole, which is the delta H vaporization. Okay, we want to convert that to joules per mole, so multiply it by 1,000. All right, the second step is to convert all your temperatures to Kelvin. So what is the formula to convert degree C to Kelvin? Okay, adding 273, right? Okay, add 273, we get it to Kelvin. So that's what we did here. So we have T1 and T2. Okay, next thing is to plug everything in. So P1 is 100. P2 is what we're trying to find. Delta H vaporization is this number, so we'll put it in here. R is a constant. I'll give you that number. We'll put it here. 1 over T2 and minus 1 over T1. Okay, so we plug everything in. T2 goes here. T1 goes here. All right, so do we know how to calculate this and solve for P2 now? All right, so let's go use our calculator. Okay. If you have your calculator out, we can do it with me. Okay. So we'll do 1 over 3365. Okay, so get your calculators out. 1 over 336.5, okay, minus 1 over 307.9, so put parentheses on it. 1 divided by 307.9, close those parentheses. Okay, you get this wacky decimal, okay, times 39,300, and divided by 8.314. minus 1.304. Okay, I added some extra digits. So natural log in the brackets 100 over P2 is equal to negative 1.3048. Okay, this whole thing equals negative 1.3048. All right, so to get the natural log out, you do the inverse natural log. Okay, the inverse natural log is e to the power of x. Okay, this is the extent of the math that we will do in this course. Bless you. Okay, inverse natural log is the same thing as e. So e to the power of natural log of 100 over P2 equals e to the power of negative 1.3048. If you take e on this side, you have to take e on the other side. So e to the power of natural log of this is what? It's this itself. Okay, e to the power of natural log of any number is the number itself. Okay, let's take a number 2, for example. Okay, I'll have natural log of 2. Natural log of 2 is that. But now what I'll do is I'll take the inverse natural log. So you do shift, inverse natural log, and then this answer. And what should I get? I should get back my 2. So these are like, inverses, literally inverses. So e to the natural log of 100 over P2 is 100 over P2. E to the power of, so this is what you'll do on your calculator. Okay, you're going to do shift natural log, not the natural log, but the shift natural log, minus 1.3048. Close the parentheses, and you get 0.271. Okay, well, put some extra digits there, 0.2712. And now we'll solve for P2. Okay, this is vapor pressure P2 at the temperature of 336.5. So how will we do that? Okay, we'll cross multiply. Okay, so we'll take the P2, move it up. We'll take the 0.2712 and move it down. So P2 I'm getting to equal 100 divided by 0.2712. And this should be our answer. About 368.7. We'll just go with 369. And what do we need to do here? Okay, don't write 369 alone by itself. What do we need to add? The units in its millimeters of mercury. Good. So this is our answer. So ethanol, okay, which is a alcohol functional group, at 34.9 degrees C, it has a vapor pressure of 100 millimeters of mercury. We raise that temperature to 63.5. If you raise the temperature, what also goes up? The vapor pressure. And here it has gone up to 369. This makes sense. If you raise the temperature, you have more molecular motion, more kinetic energy, and more of the molecules can evaporate. And if more of molecules can evaporate, more molecules can also condense. When they condense, they can form a vapor pressure. All right. So this is how you do a problem like this. So on the exam, something like this, just with different numbers. I'll give you the equation, and I'll give you all these constants. All right, shall we move on here? All right, let's move on to page 14 of our notes. All right, so vapor pressure is one phase change. Another phase change is evaporation and condensation, which gives rise to vapor pressure, is another phase change. One more phase change that I want to share with you guys is a liquid going to a solid. Okay, a liquid going to a solid is called freezing. And what's the back called? The back is called melting. Okay, so we have something called the delta H fusion. Okay, delta H fusion. So it's the energy involved to melt 1 mole of a substance. Okay, the key word here is 1 mole. So this is the next phase change. Okay, we already did one phase change. Now we're going to do another phase change. So melting is the energy required to melt 1 mole. Okay, that's the key word here, 1 mole of a substance. Okay, what are the units? Kilojoules per mole or joules per mole. It's the same thing as delta H vap. What was delta H vap? Or delta H vaporization? Okay, that was the energy required to do what to 1 mole of a substance? Vaporize. Okay. Same thing, kilojoules per mole or joules per mole. Right. So here we have some values. Okay, the melting points of different substances. This is the delta H fusions. This is not something you need to really memorize. But look at this value of water. Okay, what do we say about water that makes it special? Okay, what is the main IMF for water? It's polar, but what else can water do? Hydrogen bonds. So you're looking at a really large value here of about 6,000 joules per mole. Okay, to melt 1 mole of water. Anybody know how much 1 mole of water weighs? How much does 1 mole of water weigh?
Like 18.
Correct, it's 18. Okay, remember how did we do that from Gen Chem 1? Okay, H2O, we have 16 from oxygen and about 1 from hydrogen. But why do we multiply this by 2? Because we've got 2 hydrogens. Remember this? Okay, 1 mole of water is about 18.0 something grams. Okay, 18.04, 18.02, however decimals, however accurate you want to be. So to melt 1 mole of water, to melt 18 grams of water, same thing. Okay, you need about 6 kilojoules. Or 6,000 joules. Okay, and most of that energy is going to break up what?
The hydrogen.
Most of the energy is going to break up the hydrogen bonds. That's correct. Very good. All right, how about another phase change? Solid going to vapor is called sublimation. And this is, we're going to call delta H sub. Okay. Okay, energy required to sublime vapor to a solid. You skip the liquid. Vapor to solid, no liquid in between. Vapor to solid. The energy required to sublime 1 mole of a substance. Okay, the key word here is 1 mole. And just like before, we're talking about kilojoules per mole or joules per mole. Okay. So delta H, So we have energy required to vaporize 1 mole of a water or anything, energy required to melt 1 mole of water or anything, and the energy required to sublime water or anything. By sublime, we mean the energy required to go from vapor straight to solid. All right, let's go to the next page here. So if energy of, the energy to vaporize 1 mole. Okay, so that is, what is vaporization? Okay, we're going from a liquid to a gas. Okay, that energy, to do that, we'll call it delta H vaporization. Right? Okay, what is delta H fusion? Melting, so that's the energy required to go from solid to a liquid. That energy we'll call delta H fusion. And let's see here. If, let's say we add these two equations. Okay, let's add these two equations. If we add these two equations, okay, we will add the delta H vaporization plus the delta H of fusion. And we add the energies, and we add these two chemical equations. The liquid on the reactant side cancels with the liquid on the product side, and we are left with solid going to gas. But what is solid going to gas? Sublimation. We'll call that energy sublimation. So delta H sublimation is equal to delta H vaporization plus delta H fusion. Okay, so that's a neat little equation you can keep in the back of your mind. Okay, so now let's switch gears here and talk about the heating and cooling curve of water. So apparently, this is several years ago, I was told that this is something that was covered on the MCAT. So for anyone that's interested in taking that exam to go to medical school, apparently this is one of the topics they cover. I do not know. I don't know if they do or not, but it's just what I've heard. So this is the heating and cooling curve of water. So on your x-axis we have time, okay, for this type of curve. Okay, so time is always marching forward. Time is always marching forward. And then temperature is on the y-axis. Now, if we raise the temperature, this becomes a heating curve. Okay. If we cool the substance down, what will it become? Not a heating curve, but a cooling curve. So we have a heating curve and we have a cooling curve. Okay. It depends whether you're heating the substance or cooling the substance. So we can do this heating and cooling curve for anything, but let's just try it out for water. Okay, let's try it out for water. So let's pretend we're at some temperature for water. Let's say we are at minus 20 degrees for water. What would water be at minus 20 degrees C? Solid, liquid, or gas? It will be a solid ice, okay, like in your fridge. But we'll heat this water up. Okay, we'll heat it. So we heat until we get to this point here, point A. Okay, what happens at point A as we continue to heat? We're continuing to heat, but something strange happens. We heat, but the line is like a flat over time. Over time, the line is flat. So what coexists at this point, AB? Two phases exist. One is a solid, and one is a liquid. Okay, can anybody guess what temperature this is at? 0 degrees C. Okay, at 30 degrees C, you probably have all liquid water. Okay, so this would be 0 degrees C. Okay. So we have two phases here, okay? A solid and liquid at 0 degrees C. This is called the normal melting temperature. Okay, normal melting temperature. Normal meaning 1 atmosphere. Normal at 1 atmosphere. So water at 0 degrees has both solid and a liquid. Okay? We will continue to heat. We will continue to heat. What must the heat overcome to get over AB? It must overcome the phase transition. Because right here at AB we have a phase transition. And what is the phase transition of? Solid going to what as we continue to heat? As we continually heat. What happens to this solid? It's becoming more and more liquid. So we have to overcome that phase transition. What is the phase transition we must overcome? Solid going to liquid. Okay, we must overcome, or we must add a delta H fusion. This is what must overcome to get over AB. Okay, delta H fusion. Okay, what is delta H fusion for water? Anybody want to look at the book or of our notes? Okay, to get over AB as we continue to heat, remember we're heating now, delta H fusion for water, 6.01 kilojoules per mole. So this is what we must overcome. So finally, we heat, we overcome B, okay? We overcome B, and now we continue to heat, continue to heat. What happens here? We are all liquid, but we will continue to heat, keep on heating. Heat some more until we reach a point where we get both C and D together. It kind of comes as time moves on. This plateaus, this gets flat. So what are the two phases that exist here? Liquid and vapor. Okay, can anybody guess what temperature this is at? Okay, what would this temperature be? 0. And then what will this temperature be where you have both liquid and gas? 100 degrees C. Okay, this is called the normal boiling point of water. Normal boiling point, where we're talking about normal being 1 atmosphere. So what must we overcome to get past D? Or what must the energy that must be added to overcome D or overcome CD, the liquid and vapor equilibrium? What's the energy we must overcome? Okay, we must overcome a phase transition. And what is that phase transition? What is that phase transition to overcome for water as we heat? What must water overcome? The delta H of vaporization. Okay, that's a phase transition. So AB is a phase transition, where you must overcome delta H fusion. CD is a phase transition, where you must overcome delta H vaporization. So what is that for water? Anybody remember from our notes? I'm getting 40.79. Okay, we'll go with 40.79, page 12 of our notes. Okay, 40.79. And then after we add enough heat over time, time is continually marching on, over time, we overcome CD. We become more and more vapor until we become exclusively all 100% vapor. So you have to overcome 2 transition states if you want to go from minus 20 to, 120. Okay. What are the two phase transitions you must overcome? fusion and vaporization. So that is a heating cooling curve, but this one is water. Okay, water is pretty easy because we know at 0 degrees we have a phase transition, overcome that. And at 100 degrees you have a phase transition that you must overcome. All right, does anybody remember a little bit of thermodynamics from General Chemistry 1? Okay. No? Okay. Maybe. A little bit? Okay, those are good answers. Except the one that said no. But that's okay. I'll tell you. I think, to be honest, I don't remember thermodynamics myself, so it's okay. It's totally fine. So we're adding heat here. Okay, so heat is lowercase q. Okay. Heat is lowercase q. So if we heat something, for those of you that are slightly reminiscent of thermo in Gen Chem 1, if you heat something, what is the sign of the heat? Positive or negative? If you heat something, you're adding energy to the system, and when you add energy to the system, that value becomes positive. When you add energy to the system, that energy becomes positive. Okay. When you cool something, okay, where's all that heat going to?
Outside the system.
And what do we call outside the system? We call that the surroundings. So if it gives off to the universe, if it gives off heat to the universe like it does in cooling, that Q becomes negative for the system. Okay, the system gives off heat to the universe, to the surroundings, and that Q is water. So let's say I have warm water here, hot water. Okay, what happens after 3 hours? Where does all the heat go? Surroundings. So the system, the water, is negative because it releases heat. It releases heat to the outside. Okay? So if you release heat, you are negative. If you add heat to your reaction to the system, you are positive. All right? So that is something I just want you to keep in the back of your mind. All right, we'll do this problem here. Okay? And you'll see something on the exam. And I'll give you the equations and I'll give you the constants. Right? So calculate the heat released when 68 grams of steam at 124 degrees C is converted to water at 45 degrees C. Water at 45 degrees C. Okay, so how will we do this? So first of all, I'll give you this equation. Okay, heat is Q and the equation is ms delta T. Okay, ms delta T. Okay, remember this maybe? S is specific heat. C is heat capacity. Okay, slightly, kind of the same but slightly different. Okay, so ms delta T. Okay. So S is what's called specific heat. Okay, it's the heat required to raise 1 gram of a substance 1 degree C. Okay, if you know that, good. If you don't, that's okay. I'll give you that constant anyways. But it's the heat required, not something you need to know for any exam, but to raise 1 gram of a substance by a temperature of 1 degree C. Heat required to raise 1 gram of a substance by a temperature of 1 degree C. It's very specific for 1 gram. Okay. All right, so let me give you some constants. So these are constants. That's why you don't need to know this. The specific heat for water vapor or water steam. I got this from the book, or I don't remember where I got this constant from, but it's 20.3 joules over degree C. Okay, so it takes 20.3 joules of energy to raise 1 gram of water by 1 degree C. All right, so that's water as steam. Water as liquid. Okay, the specific heat of water is 4.184 joules over grams degrees C. Okay, so water as the liquid state, it takes 4.184 joules of energy to raise 1 gram of water as a liquid by 1 degree C. These are constants. You do not have to memorize them. Okay. And I believe we also have ice, steam, solid, liquid, and gas. So we have ice or solid water. Its specific heat is about, I believe, 1.99 joules over grams degrees C. Okay, so it takes 1.99 joules of energy to raise the temperature of ice, 1 gram of ice, by 1 degree C. Okay, so these are constants. These are not something you need to know. So they go into this equation here, Q equals ms delta T. Anybody know what delta T is? Change in temperature. Okay, it's the final temperature minus the initial temperature. Right, so with this equation and with these constants, we should be able to solve this problem. Okay, so let's go ahead and do that. So it says calculate the heat released. So what would the value of Q be, positive or negative, if it releases it to the outside? Okay, it should be negative. Okay, and we have a mass of 68 grams of steam at 124 degrees, and we need it. How much heat is released to the outside universe, and going from 124 to 45. So this is not. Let me tell you the wrong way to do it. Okay, the wrong way to do it is by plugging everything in. Okay, 124 minus 45 times 68. And specific, well, which specific heat are you going to use? Okay, which specific heat are you going to use? So you cannot plug it in. Okay, what you have to do is break it into steps. Okay, so first off, we're going from, okay, we're cooling, right? We're cooling. So we start off at 124 degrees, and we cool it to what temperature? 45. We're starting out at 124 degrees C. And we're cooling. Okay, we're cooling to what temperature? Cool, 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 cool. Some more cooling, more cooling, more cooling, more cooling, more cooling. What do we cool it to? 45 is somewhere here. 100. Okay, 100. Why do we stop at 100? Because what happens at 100? The phase change. So step one, we got to break it into parts. So step one, we're going to cool from 124 to 100 degrees. So that's going to be Q is equal to mass. What's the mass of water? Grams. What's the specific heat? What specific heat are we going to be looking for here? Okay, at 124 we're steam. At 100 we're a little bit we're at the phase change, but initially we are steam at 124. So we'll use the specific heat for vapor water, which is 20.3 grams over 20.3 joules over grams degrees C. And then what is final minus initial? Final is 100 degrees C. What is initial? 124 degrees C. Okay, so we have to break this down, break it apart. Okay, so what's 100 minus 124? That's 24, right? No, sorry. 100 minus 124. I'm way off. I'm wrong. 100 minus 124. Yeah, minus 24 times 20.3 times 68. Are you getting about minus 33,130 joules? Okay. Minus 33,130 joules. Okay, why did I say joules? Let's cancel out our units. Everyone look at me, their units, or look at the board. Grams, grams, degree C, and degree C cancel. Okay, so we are left with joules. All right, are we done? We just went from 124 to 100. Now what? Okay, we cool, we cool, we cool, we cool, we cool, cool some more, cool some more, cool much more, cool more, cool more. So what happens at 100 degrees C? As we continue to cool, okay, we're trying to go from 120 minus. We're trying to go from 124 to 45. But what happens as we reach 100? We have to overcome what? Phase change. Okay, so now we have a Q1 from 100 to 124 to 100. Now we have a Q2. What is Q2? Q2 is phase change at 100 degrees C. Okay, phase change. Okay, so this we'll call Q2. We'll put it as red here. So what is Q2? What does this equal? Okay, so what is the phase change energy? Okay, 40.79 kilojoules per mole. That's for 1 mole. But how many grams do we have? 68. So we need to convert this water to moles, and then after we convert that to moles, get the energy required to overcome the phase change in our cooling. So 124 to 100. Now we're at 100. We're continuing to cool. Once we're at 100, we have to overcome the phase change. So we have 68 grams of water times 1 mole of water has 18.04 grams of water. And how much energy is required to vaporize 1 mole of water? 40.79 kilojoules. I will convert it to joules. So just multiply that by 1,000, and you should get 40,790 joules. 1, 2, 3. Yeah, 40,790 joules. Okay, I'm just multiplying this by 1,000 to get it to joules over a mole. Okay, so we have 68 grams. Okay, 1 mole of water is 18 grams, so the grams cancel, the moles cancel. We're left with joules. So 68 times 40,790. 68 grams times 40,790 divided by 18.04. What do you guys get? I'm getting about, so this could be a mistake. We're still cooling, so what is the sign going to be, positive or negative? Negative, so don't forget the negative, okay, because we're cooling. If we were heating, what would the sign be? Positive, but we're cooling, so the heat's going to the outside. So just remember to put the positive. Minus 153,754, something like that. Joules. Okay. Don't forget the positive because we are cooling. Okay. If you're heating, it becomes positive. Since we're cooling, it's going to the outside, to the surroundings, so we have to put the negative. That's what the thermodynamics is. All right, finally we have Q3. So what is Q3? Okay, so we overcome this. We started here at minus 124, minus 124 to 100. So we started here at 124, 124 to 100. We've overcome the 100, and now we go all the way to 45. Okay, so step 3 is going from 100 to 45 degrees. So cool from 100 degrees C to 45 degrees C. So now we will do Q, this will be Q3. And Q equals ms delta T. Okay, the mass is 68.0 grams. What specific heat should we use in going from 100 to 45? 100 to 45. At 45, what is water predominantly? Liquid. Okay. So we will use this specific heat. Okay, we're not going to use this specific heat because at 45 we're not steam. We're not going to use this specific heat because at 45 degrees the final temperature, it's not ice. At 45 degrees water is a liquid. So this is the specific heat we will use for RS, and that is 4.184 joules over grams degree C. What's our final temperature? Okay, 124 to final 45. What was our initial temperature? It's not 124, but what is it? 100 degrees. Okay, so we have broke this problem down. 124 to 100. At 100 there's a phase change, and then we go from 100 to 45. Okay, this is how you do that problem. You have to break it up. Okay, the grams cancel, the degree C cancel. We're left with joules. So what's 68 times 4.184? Actually, what's 45 minus 100? 55 minus 55 times 4.184 times 68. I'm getting minus 15,648. Anybody get that? Or something close to that? Minus 15,648 joules. All right, so our total heat to go from our total heat in going from 124 degrees positive to 45 degrees of water, we add this, and this up. Okay, we're going to add Q1, Q2, and Q3 up. This is the energy released. When you cool water, initially at 124 degrees, we cool it to 45 degrees. This is the energy released to the surroundings. Right, let's go ahead and add these up and see what we get here. We'll add them up on here. Okay, so what did we get for Q1? Minus 33,130 joules. Okay, what did we get for Q2? Minus 153,754 joules. And what did we get for Q3? Minus 15,648 joules. And what is this on our calculator? Finding a hard time doing this. Minus 15,648. What did you guys get? Something related to minus 202,000?
Yeah, that's right.
Okay. All I need is one person, and that gives me the confidence that I did the calculator right.
202,542 instead of
I think that's fine. That's good enough.
0.16.
Okay. So this would be our answer. So what I like to do is actually I would like to convert it to kilojoules, divide by 1,000, and you can go at minus 203 kilojoules. And this is the answer. So on the exam, if you put minus 203, or if you put minus 202,540, that's fine. Everybody's rounding is a little different. Let's say you had to go from 124 degrees C. In this problem, you had to go from 124 to 45. What if you had to go from 124 to, I don't know, minus 45? What will you need to do? How many heats will you need to add? 4. It will be 124 degrees C to 100. What would Q2 be? Phase change at 100. What would Q3 be? 100 degrees to what? To 0. Very good. What would 0 be? Phase change. So this would be phase change. Phase change. And then finally, Q5. What would Q5 be? 2 minus 45 degrees. Okay. So if you're going from 124, not to 45, but 124 to minus 45, you have to add 5 heats. The heat going from 124 to 100, the phase change at 100, heat going from 100 to 0, phase change at 0, and then finally the heat going from 0 to your final temperature at minus 45. You see that? All right, let's quickly go over these phase diagrams in the last minutes of class. This is basically a pressure-temperature combination, phase diagrams. Okay? Phase diagrams is a pressure-temperature combo. So at a specific temperature and a specific pressure. At a specific temperature and a specific pressure, you can be solid, liquid, and gas. Okay, this is for water. This is for something else. I think this is CO2, but that's not important. At a specific temperature and pressure, you can be solid, liquid, and gas for CO2. At a specific temperature and pressure, you can straddle between solid and liquid. You can straddle between liquid and vapor. Okay? At a specific temperature and pressure, you can be all liquid. At a specific temperature and pressure, you can be all solid. Okay? At a specific temperature and pressure, you can be all vapor. Or you can be a combination of both. Right? So one more thing here before I let you go. Water is very unique because this bends backwards. Okay? No other substance does that. It bends backwards. And then this curve here, okay, you see this curve? This liquid vapor curve is exactly this curve that we saw in our notes before. Okay, it's exactly the same curve. Exact same profile. Okay, it's the exact same profile. All right, so that is a wrap of Chapter 11, so see if you can get your homework done. I don't know what date I put it due on Canvas, but you can just do your homework, check your answers, upload it. This is practice, and I'll give you your points. Right? And I think we have a lab, and I'm hoping they set it up. So it should be a fairly short lab if you've come prepared. I'll see you there at 2 o'clock.